Yeah, I don't know how that
given everything else, on top of everything going on, it's Friday the 13th, you know?
Unless they do online stuff.
All right, everybody settle down. Let's get started. Everybody settle down. All right, so let's talk about some logistics for the class, because I want everybody to be aware of as much as you can be now, between now and the end of the semester. First off, okay, let's talk about course logistics. Let's make sure everybody's paying attention. Okay, so Exam 1 corrections graded and returned. Your Exam 1 grade is posted on Blackboard. Homeworks 1, 2, 3, and 4 are posted, and as you remember from last lecture, the attendance grade is taken care of from here on out. One thing I'm not going to do is adjust the grading policy of the course. In other words, your grade will be determined based off of your attendance, your homeworks, and your 3 exams. So it's not like I'm going to throw a project in there and say, oh, we're going to do this instead or something like that. No. We're still going to have homeworks, 3 exams, so on and so forth. But your attendance grade is taken care of. Okay, so let's talk about what we're going to do from here on out. First off, you were supposed to have homework in Shear Design. I'm going to postpone that, and that'll become clear here in a second. But you all don't have a homework in here. Okay, let's be clear. And I want this to be crystal clear. I am not going to assign anything next week. Okay, the purpose of next week's cancellation is twofold. It's to get all of the faculty prepared to deliver online lectures. To be honest, I could just start posting videos and I'd be good. I can start Monday. The second is to make sure that everybody's on the same page. In other words, I don't want to start teaching on Monday and start assigning stuff next week if your sociology and your English and other classes are truly waiting. Then you're at a different pace, right? I'm going to respect that, and we're not assigning anything next week. Okay, there is one point of logistics with Steel Design, and that's you all have a homework currently, that welded homework, and we'll talk about what we're going to do about that in there. In terms of the new course operation and how we're going to do this moving forward when we come back from break, this is what I think I'm going to do. First off, I had toyed with how I was going to deliver the lectures. My initial thought was I was going to use, honestly, just like YouTube Live, just like a YouTube video, only it'd be live. But instead, I think I'm going to transition to Blackboard Collaborate Ultra for a couple of reasons. One, it looks like a number of the other civil faculty are using that. I believe Dr. Yoon is using it. I believe Dr. Waite is using it as well. So using one system makes your life a little easier instead of you having to go to YouTube for my classes and going to Blackboard for Dr. Yoon's classes or something like that. It's all in one spot. It has all the features that we need. I can present the PowerPoints. I can do problems like I do here on the screen. I can have a little camera so you all can see me. I know that's, I apologize for your suffering there, having to see me again during break. I'm kidding. But it also allows for everybody to call in, okay? And not only is there an opportunity for you to chat and type in questions as the lecture is progressing, but you can literally call in and ask questions verbally. So I think we might try that. I'm going to do the lectures at the same time that we do it here. So Monday, Wednesday, Friday, 10 to 11. And for Steel Design, Monday, Wednesday, Friday, 11 to 12. We're probably going to, the plan is now we're going to have everybody call in and then keep your phone on mute so it's not like 20 people, eating potato chips, on the phone. But if you have a question, unmute your phone and ask your question, just like you would in class. Just say, hey, Dr. Mike, could you explain this again? And we'll do this together. And I think that's what we're going to try to do. We'll try that out, see how that works. Okay? Now, what that does change, or what the only other, I think, variable to discuss are the homeworks and the exams. Let's talk about the exams first. There's going to be an exam during this period. I guarantee it. Just like there's going to be an exam during Steel Design. It's probably going to be an online-based exam, sort of like a quiz that you would take via Blackboard. I'll give you enough time to do it. You can upload your scratch calcs and whatnot, and so on and so forth. I'll give you more time than just like 50 minutes to make sure to account for any technical glitches and things like that. There's also a chance that we don't do it during the class time. Like, for instance, we might do it on Tuesday or might do it on Thursday. because there are some, I want to make sure that we're at least covering the base topics in steel design, or in concrete design and steel design. There are some topics that I'm not going to be able to dig as deep into, because I want to make sure that you're comprehending as much as possible. And so if that means I need to, tailor my lectures accordingly, I will. But I guarantee you we are going to have at least one test done online for both classes. Okay? The final, we will see about the final. We might be here, we might not. I don't know. But I'm going to schedule accordingly. Depending upon where we get today, I will send you all an updated lecture schedule and an assignment schedule next week. That's the only thing I'm going to send you next week, is that, and maybe logistics for getting onto the online lectures. One other thing that might change is the homework schedule. As you all know, what I usually do in my classes is I have these really, really big homework assignments when we finish a module. Like, we finish bolted connections in steel, and then here's the bolted connections assignment. And it's this big, to-do assignment. I am very seriously considering not doing that. And instead, after each lecture, giving you a little, one problem, one short problem, do the following lecture. And I'm doing that to sort of, make sure that you're attentive and watching the lectures on time, but B, I think the net effect of that is you'll probably end up doing a little bit less work between now and the final. And I'm not trying to make it easy on you, but at the same time, it's going to be weird for everybody. So I'm thinking, let's try and be cognizant of that. So instead of these 40-point assignments, 50-point assignments, you may get a 5-point assignment on Monday, do Wednesday, or 10-point assignment on Wednesday, do Friday. So we'll still do homework. It'll just be different probably. All right? Any questions on that? Now, one thing you'll notice, if you go to Blackboard, so here's the Blackboard page for the class. If you go to course content, you're going to see a new folder that says online live stream lectures and new course operation. If you open this link and you click this, it says Blackboard Collaborate Ultra. This is what you click to access the lectures. So for instance, you click this, you will see this dialog box pop up. You'll see a scheduled session. I'll set it up to where you can connect a little bit early to the lecture. So if the lecture starts at 10, you should be able to connect at 9:45, anywhere between 9:45 and 10. We'll start at 10 and we'll go to 10:50. I will record those lectures, so you should be able to access them, in case you aren't able to make it. But let's be clear, even though we're not meeting face to face, my way of operating this is it's Monday at 10 o'clock, we're having class. So everybody okay with that? Yes, sir.
So you may have mentioned it before I even came to the room, but maybe. So will there be a way over the live stream for us to communicate back and forth with questions and stuff?
Yes. Okay. Do you eat potato chips?
Sometimes.
Okay. Then this is going to go for you. When you log in, there is a phone number that you can call into. And so everybody in this room could call in, and we would all be on a conference call with everybody. So what I'm going to ask is that everybody do that, but you mute your voice. But if you have a question, unmute, say, hey, this is Brandon, I have a question. And then just ask. So that way everybody can ask. There's also the chat window as well. If we have some technical glitches, we'll work it out. We'll go towards, we'll record a lecture and figure it out later. But that's the plan moving forward. I will send you an updated lecture schedule and homework schedule sometime next week. But the homework schedule literally might just be, it's Monday, here's an assignment, do it Wednesday. Wednesday, here's an assignment, do it Friday.
There's a way to raise your hand on the module too.
I was saying you can do it either through the, because that'll allow you to type the question, right? Like in a chat box. Any questions?
Do we do that call-out number like this?
Yes. It's a phone number with, you say you dial it, it says, please enter your PIN. You enter the PIN and boom, you're in the class.
Does it give us the PIN?
Yes, it gives you the PIN.
So
like for instance, watch this, watch. Let me, I want to get to the topic today, so I don't want to spend too much time on this, but we might go to 10:55 or 11 as a result. It's not like you have, I know the guys who teach us the class next. So watch this, watch. Everybody pay attention. So, for instance, when I create a session, we'll say lecture 27, and I go in and pick dates and whatnot. It gives you the pin, or it gives you the call-in. So this would be the call-in, that would be the pin, and you would just call that number and call in. Just mute your mic so that I don't hear 20 people chewing on potato chips. Of course, this phone isn't going to work because I'm not creating the session. All right, does that make sense? So like I said, I will send you some information next week when I finalize the schedule, but what I would like to do today is keep on trucking and talk about shear, okay? I want to try and make some progress there, so we're going to go at least till 10:50. If I go a couple minutes over, I apologize. But what I want to do is I want to go through yes, sir.
So this all starts after spring break?
After spring break. We are not doing anything next week.
Oh, that's sad. They did officially cancel the Virginia conference.
Yes, they did, yeah. Although that isn't too surprising, I was going to send something out to the students here in a little bit, but I didn't have time between now and class, but yeah, it is officially canceled. Let's get right into it, okay? So, what I want to do today, my goal for the lecture today is to do a shear design. And we're going to do a simple problem. This is a simply supported beam with a uniformly distributed load. I went ahead and already factored the load. This is a lot of load. This has got a lot of oomph on it. This has 11.5 kips per foot. It's pretty intense. It's a 20-foot long beam. It's simply supported, 4 KSI concrete, 60 KSI steel. And what I want to do is I want to do the shear design. And by the shear design, what I'm talking about is laying out the stirrups, okay? So I'm sort of talking about this, so how do I lay out the stirrups across the span? And so I'm going to walk you through how to do that. It's really not that hard, it's just a little bit unique, okay? So this is example 13. All right? I think everybody in here is also in steel, right? Except for you.
Oh, nice.
But I'll see you in next time anyways. Okay, so let's look at this beam. Now keep in mind, FC prime is 4 KSI. Now we're dealing with normal weight concrete. Now normal weight concrete means that lambda is 1. Okay, we have a yield stress of 60 KSI. Let's see, we know our beam has a width of 16 inches and a depth of 25 inches. We also know that we are being subjected to a factored load. This has already been factored. Already has dead load and live load in it of 11.5 kips per foot. Okay. We know that the beam is 20 foot long. Okay. Now, let's make sure that everybody's crystal clear on what's going on from an analysis standpoint. So I have a simply supported beam and I have a uniformly distributed load. So here's the beam. So 11.5 kips per foot. This is 20 foot long, right? And so would you agree that the shear diagram is going to look something like that? Would you agree with that? That's going to be our shear diagram. Now, the first step of this problem is going to be produce this shear diagram, but it's going to be much more detailed than what we have here on the board. Okay, first off, I'm only going to focus on half of the shear diagram. And 2, there's going to be a lot more values that go on that shear diagram. We're going to need the equation for the shear diagram and what have you. Now, let me turn the lights down so it's a little bit easier to see the screen. Okay. Lastly, we know this problem has number 3 U-shaped stirrups. So what that means means is we know the area of a number 3 is 0.11 square inches. So what that means is that the area in shear is 0.22. We did that last time. Remember when you have stirrups, when you have a beam where you've got steel and then the stirrups go like that, that's a U-shaped stirrup. So if I cut a section, how many bars am I going through? 1, 2. So AV is 2 times the area of the bar. So since the bar is 0.11 square inches, A sub B is 0.22. Everybody okay with that? All right, good. Now, step 1 is to construct a shear diagram. This is an involved step. Okay, so let's look at this. Can anybody tell me what those reactions are?
$115.
115, right? And how do you do that? You take 11.5 kips per foot times 20 foot, so that's the load on the entire beam, and you cut it in half. And so that's 115 kips. Is everybody okay with that? Bless you. So from an analysis standpoint, would you agree that this point right here is 115? And this is minus 115. Maybe I'll just sort of write it like that. Maybe I'll just hover it above. Is that fair? Now, let's see if you all remembered this from structural analysis. What is the slope of that line?
Excuse me.
How about that? It's the load, remember? The slope of the shear diagram is the magnitude of the load. And so the slope is minus 11.5. Why is it minus? Because it's going down, right? So would a fair expression, would a fair statement be that therefore the shear as a function of x is 115 minus 11.5x? Would that be a fair statement? So what I have here is an equation for the shear diagram. Now, for this expression, I left a lot of units off. Help me out. Let's do this. Let's just keep this simple. Let's just call this VU. Help me out. For this equation, for this to work out from a unit standpoint, what are the units for x? It's 11.5 kips per foot, so x has to be in feet, right? And then shear comes out in kips. Is that a fair statement? Now, so what I have here is I have the shear as a function of x, okay? What I am now also going to do is I'm going to flip that around, and I'm also going to say, well, what about this? What about that? Would you agree with that? Just take the equation, solve for x. Okay? these equations have specific purposes, okay? The upper equation will tell me what is the shear anywhere on the beam. But the second equation will tell me if I'm looking for a given shear value, where does that occur, okay? Both are critical from a design standpoint, okay? And you're going to see why here in a second. All right, everybody with me on this? Now, we could be a little more exact in our statics and cut a section, but we did that in our last example. I kind of want to just sort of make sure I'm making progress. So everybody's okay with these equations? All right. Now, next thing I want to compute is some concrete capacity. And you're going to see why. So, VC, if you remember the equation for VC is 2 lambda BWD square root of FC prime. In other words, I'm trying to design the stirrup layout, how much steel I need. Well, I'm not going to have an adequate understanding of how much steel reinforcement I need unless I know how much the concrete can carry on its own. So that's what VC is. All right, so this is 2 times 1 times 16 inches times 25 inches times the square root of FC prime. Remember, when you see a square root of FC prime, you put in PSI, you get out PSI. So, help me out. Some of your crunching buttons, for those of you that aren't crunching buttons, what are the units going to be when you calculate all this out? Pounds. It's a shear, so it's got to be a force. And it's in PSI, so it's pounds.
50,000, 596.44.
So we'll say 596. Pounds, which also equals 50.596, sorry, 0.596 kips. Okay? So, next thing I want to do is I want to compute phi VC. What is phi for shear? 0.75. Okay, so what is that?
37.947 kips.
Say it again.
37.947 kips.
So we'll say 37.95. And then the last thing I want to compute is half of PVC. So what's half of PVC? It should be like 18 something, like a high 18, almost 19.
18.97.
97. Everybody good? Okay, I don't want to just like be computing values for the heck of it. I want to refer back to the notes and make sure that you all know what I'm doing. If you remember your procedure for shear design, the first thing you need to do is construct the shear diagram. And so when you're constructing the shear diagram, you have to figure out where your shears are bigger than that, where your shears are between these two values, and when your shears are smaller than that value. Hence why I computed the PVC and the half of PVC. Does that make sense? So I didn't want to just be doing stuff for the heck of it. Okay? Now, here's the thing. Okay? Let me look over here. I'm going to cheat and use this. I'm going to use this. Okay? Let me blow this up. Don't worry, I'm going to draw a much neater one here in a second. But let me blow this up a bit. So all right, so this is 115, right? Okay, and this is x equals 0, right? Now, how long was the beam?
20 feet.
20 feet. So this is x equals what? 10 feet. All right? Now, I have a PVC value and a half a PVC value. Now, PVC is what, like 37.95? So if this is 115, that's about right there. Maybe that's PVC, and maybe This is a half of PVC. Is that fair? So if I'm going to construct this shear diagram and be a little bit more detailed, I need this and I need that. Right? Okay? That's one thing I need to figure out. The other thing I need to figure out is this. If you recall in the notes when we were discussing this, we can always begin our shear design at a distance d away from the support. Okay? We don't have to start our shear design with this value. We can instead start it maybe right here. Now, where is that? We know that this is D. What we now have to figure out is this. So in order to properly construct our shear diagram, we need three values. We need to know what this is, and we need to know what these are. Okay? Remember how I derived those two equations in the blue boxes? Now you can see where they're both becoming useful. Because I'm going to use this equation to figure out VU star, and this equation to figure out where PVC and half of PVC are. Sound good? So let's go ahead and do that. All right, so we will call this important plot values.
Is it silly of me to look at it and see it as similar triangles though?
You basically are.
Would we be able to just do it that way, or is it?
Absolutely. That is absolutely correct. You could use a similar triangle expression to do that. The one thing to be cautious of is, what if you have a distributed load? But you also have point loads. So what happens is, if you plot that shear diagram, whoop, whoop, whoop,
Yeah.
you know, so on and so forth. So just be wary of what you're doing. But can you use similar triangles? Absolutely. Just as long as you're reflecting the right distances accordingly. Like X has to be measured from the left.
Right.
But yes, you can. Sound good? So what we're going to say here, first off, we're going to do VU star. So that's VU at X equals D. So I'm going to use the first expression. We'll say 115 minus 11.5. And what was D?
16 inches.
No,
25.
25. But you're right what you were getting ready to say. This is 25, but that's 25 inches. So you need to multiply that by 1/12. Okay? So if you want to say kips, kip per foot, so that's inches to feet. So you're exactly right. So what does VU star come out to be? Bless you. Bless you. Anybody got a value for VU star?
91.4.
Do I have a second on that? Bless you.
Thank you.
So 91.04 kips. Next is X at VVC. And so what I'm going to do for that equation is I'm just going to plug and chug into, bless you, I'm going to plug and chug into the second equation, but where it says shear, I'm just going to plug in VVC. So it's going to be 37.95 kips minus 115 kips over negative 11.5 kips per foot. Bless you. So what do I get for an answer
I
here?
got 6.7 feet.
6.7 what?
I'm gonna say, yep, feet. Is that
Feet. No, that's correct. Second?
Yes.
Okay, now, what I am gonna do though is convert that to inches, right now. So that times 12 is what?
wrong?
80.4 inches. Okay. The reason why I'm converting that to inches is because when I lay out stirrup spacing, I'm gonna space my stirrups out like in 4 inches, 6 inches, 8 inches. So having these distances in inches is gonna make sense here in a bit. And last, what happened there? X at half of VVC is 18.97 kips minus 115 kips over minus 11.5 kips per foot. I'm a little, just extend that page. And that equals what?
8.35 feet.
8.35 feet, which is what?
100.2 inches.
100.2 inches. Okay, so what do I have here? I have this is 80.4 inches, this is 100.2 inches, and instead of this saying is X is 10, I'm going to say 120 inches. Does that make sense? So, from a design standpoint, this is what our shear diagram is going to look like. And so, bear with me. This is going to be a little bit of a big plot, but it's kind of going to be repeating what is there on the screen. Okay. So this is, on this axis is the shear in kips. And this axis is the distance in inches. And so the shear diagram looks like that. But what we're going to do is sort of draw it like this. So bear with me. That's how we're going to draw it. In other words, I know full well that it continues. So I know this is 115 kips, but I don't care about that. I only care about this, which is 91.04 kips. So that stuff that trails up, don't really care about it. And recognize that this line right here, that is the center line of the beam. Last, we've got our distances here. I know that this is X equals D, which is 25 inches. And I know that I've got this going on. This one. This is, go away. So this is BBC, which is 35 point, what was it? 37.95. This is 37.95 kips. This is half of VBC, which is 18.97 kips. And this X equals 80.4 inches. X equals 100.2 inches. What do you think? Now, The next thing I'm going to do is I want to make sure, so is everybody okay with constructing this? Now, what I want to do is I want to go back to this part right here. So remember, anywhere that the shear is bigger than PVC, we have to place stirrups for capacity. So we definitely need stirrups in this region, right? This is section 1. Section 2 is this region. This region is where the concrete by itself has enough capacity to carry the shear, but the code says, I don't care, you're still putting stirrups there. So here, we ought to be using the maximum spacing. But what about this region? What can you tell me about this region? We don't need any stirrups. Okay, so what I'm now going to do then is I'm going to go to my shear diagram, and I'm going to sort of indicate that accordingly. So I'm going to say, okay, no stirrups. Here, right here, this is stirrups required. And this is use S max. In other words, we don't need stirrups, but the code says we have to put them there, so I should be using S max in that region. And we are going to use S max in this region, but we might actually use S max a little bit over here as well. And you'll see where that comes into play. So what's the takeaway? We should be placing stirrups from x equals 0 to x equals 100.2. So far, so good? All right, does anybody have any questions so far? Okay. All right. Now, step 2 is to figure out the starting S value. Now, how do I do that? I use the following equation. And what I do is, so keep in mind, there's nothing magic about this equation. All this is saying is PVC, and then VS is AFY D over S, and just solving for S. And so what I'm going to do is I'm going to use my starting S value. Although my starting S value would basically be, I'm going to design for the highest shear. The highest shear is not that, it's this, because this is where we start the design. So I'm going to use that shear value and figure out how many stirrups, like what's my stirrup spacing required to resist that shear. All right? And so is everybody okay with this? Like I wrote the equation out a little fast. Do I have an answer for me?
4.66.
4.66. Okay. Now, I'm going to go ahead and tell you, okay, first off, does that mean we use S S is 5 inches? No, you always round down. Okay, so that's point 1, you always round down. And so then we get into a question of, well, do I use 4.5 inches or do I use 4 inches? And we'll tell you, use 4. The reason why is because the math that we're about to do becomes a lot easier. You can do it in your head a little bit easier if the numbers are whole numbers. So use S is 4 inches. Okay. Now, I want to figure out the maximum S value. Okay, so we've got S is 4 inches, then we have, so how about this, Let's do S required is 4 inches. Now let's figure out S max. So, in order to figure out S max, we have 2 different equations and we have to look at both of them. So S max 1 is the minimum of D over 2 or 24 inches, which is the minimum of, what was D, 25? 25 over 2 or 24 inches, which is what, like 12.5? Then last, S max 2 is the following. Excuse me. All right, before I plug and chug that, can somebody tell me over here on the left, or on the right over here, 0.75 square root of FC prime is 0.75 times the square root of 4,000. What is that?
47.4.
So what's the maximum, that or 50? 50. Okay. So on the bottom, I'm just going to have 16 inches times 50 psi. And on the top, 0.22. And then what's FYT?
60,000.
Exactly right, 60,000 psi units. And so what does this come out to be? 16.5. Do I have a second on that?
Yep.
So, which one of these controls the design? 12.5 or 16.5? 12.5. And instead of using 12.5, what am I going to use? 12. So, S required is 4, S max is 12. So, let's use S is 12 inches. Okay. All right. We're going to do this design and then we're going to call it, okay? And if I go a little over, I apologize, but this is kind of important. Okay. All right. Is everybody with me so far on the design process? Okay, so let me explain what's going to happen. Okay, so here's the beam. Right? So the idea is that we're going to kind of use 4-inch spacing, and then there's going to be a point where we stop using 4-inch spacing and we start using 12-inch spacing. Right? Remember, when you're looking at a shear design, when you're looking at a beam, you start out with like really, really tight spacing, and then as you get closer to the middle, you start using wider spacing. Right? So we need to figure out when we can start using S equals 12. Okay, so step 4 is going to be determine the range for S equals 12. And let me show you how we're going to do that. Would you agree that if we used 12-inch spacing, that the capacity provided by those stirrups would be calculated like this? ABFYD over S. So ABFYD over S, when we compute that out, and I know we're running out of time, so I'm just going to do that one for you. That's going to come out to be 27.5 kips. If we use S equals 12 inches, that's V sub S. And if that's V sub S, phi VN is phi VC plus phi VS. So phi VC we already know is 37.95 kips plus 0.75 times 27.5. Plug and chug that and you get 58.58. Everybody with me on this? So would you agree that if I used S equals 12 inches, this is my capacity provided by the steel, and ultimately this is the entire capacity of the section? So my question then is, where does this value occur on the shear diagram? Well, what was VBC? It's like 37.95, something like that. So it's probably somewhere like here. How do we figure out exactly what it is? Exactly. So the X formula that we derived earlier is, how did I set that up? It was 58.58 kips minus 115 over 115, or negative 11.5 kips per foot. What did that come out to be? Say it again?
4.9.
4.9? And how many inches is that?
58.87.
So 58.9 inches. Would you agree with that? So, all right. I want to show you then how we design. And then we're going to call it. I know we're running over, but we're right there. Okay. It is very, very typical that whenever you're starting a design, that you place your first stirrup 2 inches away. That your first stirrup's at 2 inches from the support. The idea why is that, okay, what was our S required? 4 inches? So the idea is like, here's your concrete beam, here's the support. So that's sort of the line for the support. The idea is that you place your first stirrup at 2 inches away, because the idea is you have another one back here. So the idea is like you have a continuous start to your spacing. So 2 inches is very, very common spacing for your first increment. So watch what I'm going to do. I'm going to place the first stirrup at X equals 2 inches. Then I'm going to use 4-inch spacing until when? What's that? Exactly right. I'm going to use 4-inch spacing until I don't need to anymore, which is 58.9. Then I'm going to use 12-inch spacing until when? 100.2. So what's my design? Watch this. One stirrup at 2 inches is going to put me at x equals 2. So now here's where you got to use a little bit of mental math. How many stirrup spacings at 4 inches should I use? Well, if I use 10, that's 40 inches. So think, my first stirrup here is at x equals 2. So 4 inches, that's x equals 6. Another 4 inches, that's x equals 10. See what I'm doing? So how many stirrup spacings do I need to use to where I get to this point right here? Think about it. 14. Okay, so if I use 14, what's 14 times 4? What?
56.
14 times 4
This
is 56.
Yeah.
And 56 plus 2 is what? 58, so it's not quite enough, is it? I need one more, right? So I'm going to put 15 at 4 inches to get me 60, and that'll put me at x equals 62. Does that make sense? Because if I did 14, that would put me at x equals 58, but I can't stop at 58. I have to stop at 58.9. So I can put one more stirrup to get me past that leg. Does that make sense? So now, if you understand that, how many stirrups at 12 inches am I going to use?
So you exactly need a little over 3.
Well, 3, so let's say I did 3. So 3 times 12 is 36, right? 36 plus that is what? 98, right? 98 won't get me here, right? So I got to use 4. So 4 at 12 is 48 inches, and so 48 plus 12 is 110. So that's 20 stirrups. At 110 inches. Now, how many stirrups are going to be in the entire beam? No, because that's only the midspan. So there's another 20 on the other end. So 40 stirrups total. What do you think? I know I went through that kind of fast, but that's a little different, isn't it? So what's your answer? That's your answer. So the idea is, okay, I've got my first stirrup at 2, and I do 1, 2, 3, 4, 5, 6, 7, all the way to 15, and then I do 1, 2, 3, 4, and then I'm done. And that is the design. That is the stirrup design for this beam. What do you think? That's a little bit different, but that's kind of a new process. That is how to design for shear. The only way that we can improve that is to maybe add like a 6-inch spacing or an 8-inch spacing. And the only reason you would ever want to do that is if it would reduce the total number of stirrups. But there's a point when it's like, okay, well, how much should we reduce it? You know, there's something to be said for simplicity as well. Does that sound good? Okay, let me go ahead and stop the recording.